beginning, detailing all the proceedings of the rectilineator experiment. The location of the Crescent Geodetic Survey was over a straight patch of sand on Naples Beach, Florida, minutes from the Crescent commune. The rectilineator experiment, invented by Morrow, was a geniusly simple apparatus consisting of giant 12-foot sectioned T-squares lining up together in a leapfrog procession over a long distance to form a perfectly straight air line. If done accurately, it would determine the direction of the curvature of the Earth, if any. In other words, if the initially leveled airline would continually rise the further down it went, the Earth would prove to be convex, just like the Copernican system proclaims. If the line continued at the same height, the Earth would be proven to be flat. And if the airline would show a continual descent from the initial station, the Earth would be proven to be concave. This test of the curvature of the Earth subverts any attempts by long-distance lasers or telescopic surveys. Although these other tests are good methods to determine Earth is not convex, the rectilineator has the advantage of forcing the line, by a mechanical process, to stay rigid throughout the survey. It doesn't allow the varying bending of light, which has been proven to fluctuate throughout the day. Because of Florida's ever-rising water levels over the past 118 years since the survey, and because Naples Beach is a luxurious haven for the wealthy, the manicured beach of today looks slightly different than from the line illustrations that the Crescents provided. The survey started at the still-standing Naples Pier and extended southward for 4 1/8 of a mile. 2 3/8 of those miles were measured with the rectilineator apparatus, and the remaining 1 3/4 of a mile were surveyed by line-of-sight telescope. There's a break in the beach called Gordon Pass, and directly behind the pass is a sandbar that needed to be excavated, or scooped out in order for the descending airline to pass through the sandbar and shoot the water at 4 1/8 of a mile, where a sailboat was cast off to be used as a reference point of the termination of the projected airline into the water. The preparations before the survey could actually begin were tedious and time-consuming. A full 2 months of the complete 5-month-long project involved 1. Conducting an initial coast survey with surveyor's instruments, which involved erecting a series of stakes on the beach along the water, equally spaced at 1/8 of a mile apart, creating a 4 1/2 mile long meridian line extending north to south. These stakes were to be used as reference points for the rectilineator, but also set the locations for the caissons, which I'll get into soon. 2. Mild land excavation was necessary. The shoreline's elevation varies from about 5 feet at the pier to around 3 feet near the pass. But this proved to be a blessing for Morrow and the Crescents. Let me explain. Since the vertical standards of the apparatus were only 8 feet tall, and the calculated amount of deviation after 2 3/8 of a mile was over 48 inches, the apparatus would have had to start a good 2 feet higher than it actually did if the beach was level in elevation. But since the beach made a nice gradual 2-foot decline toward the south, Morrow could keep his beams at a comfortable height throughout the entire survey. Hence, the excavation could be simplified by simply smoothing out any small mounds of sand in the line and removing any debris. 3. 4 weeks were devoted to testing and adjusting right angles. According to Morrow, 6 series of tests were applied, and each section was reversed, end for end, and turned over 50 times on the special platform with the mechanical devices for measurement and reference. Points and the finest possible lines engraved on steel and brass plates, to which adjustments were referred, were read by means of the microscope. In this way, the very slightest variation of angles could be detected. And 4. A series of tide registers would have to be erected in the water to find a consistent datum line. Now, to compensate for the varying tidal waters, Morrow used perforated caissons, which allowed water in through small holes at the bottom. Attached to the caissons were tide staffs. The caissons stabilized the wavy water, which allowed accurate and consistent readings. Morrow states, the average of the tide levels on the Florida coast is about 3.5 feet. The mean tide level is a point midway between high and low tide levels. It was necessary to ascertain this point with all possible precision, which we did by means of a tide register, consisting of a caisson with perforations and a tide staff measure, set in the Gulf, so that its bottom was below the level of low tide and its top above the level of high tide. The perforations emitted the water from beneath at normal pressure and prevented wave fluctuations. Thus, the water in the caisson was perfectly still and only rose and fell with the Gulf tide level. When the mean tide level was obtained, it was marked upon the stationary tide register and became the fixed point to which all other measurements of water level were referred. The vertical tide staff connected to the tide register on the caisson was used to project a datum line exactly 128 inches above mean tide level. Then the geodetic level was used to transfer an exact perpendicular line over to the corresponding stake on the beach. Since the mean tide level in the first stationary tide register became a known and fixed quantity, it was taken as the basis of reference for the measure of the airline at all station points along the line. To illustrate this process, we have the staffs on both the initial station register and any given portable register along the line. Line XY is the mean tide level, which is marked as a fixed point on staff A, the top of which is the altitude of 128 inches above mean tide level, which also is transferred to the beach. They were then easily to record the same vertical altitude regardless of the fluctuating tides. Here's how. Say they were reading for a portable tide measurement 2 miles down, and the reading on the tide staff A is 12 inches above the mean tide level, leaving 116 inches of the staff sticking above the water. The line PQ is our 116-inch line. Now on staff B, they simply adjust its height to reach precisely 116 inches above the waterline in the corresponding portable caisson. This was done instantaneously with Morse code, so the reading was perfectly accurate. In this way, no matter whether the measurements were taken at high tide or low tide, or at any water level between the two extremes, the results were accurate, because the fixed point at staff A was the constant and unvarying basis of reference. Finally, when the vertical altitude of staff B was ascertained, the corresponding vertical angle was transferred to the land elevation. There were 25 tide registers in all, spaced 1/8 of a mile apart from the beginning to the end of the line, which when completed formed a line that was parallel to the water's surface. This hypsometric principle of ascertaining tidal secondary datum lines, as opposed to the first being underwater at times, was scientific and accurate. But in order for this survey to function well, the initial section had to be perfectly level, for if it leaned either up or down, even the slightest, it would give an inaccurate reading down the line later. That's why so much time and redundant measures of scrutiny were taken to make sure the first beam was perfectly level. Morrow used the finest and most sensitive spirit levels obtainable. He also hung a plumb line over each side crossarm, and he created a custom-made 12-foot-long mercurial level with fine-tuned accuracy. All three leveling procedures had to be in agreement with each other in order for the first section to be considered perfectly level. He also telescopically viewed the horizon as further corroboration and found it to be perfectly parallel with the clear-cut waterline of the Gulf. According to Morrow, the leveling was a careful, painstaking, successful work witnessed by every member of the staff, and finally pronounced perfect at 8:50 on the morning of March 18, 1897. Because of the poor quality and the scant amount of photographs and illustrations of the mechanical part of the rectilineator, with some showing differences in appearance, it was difficult to precisely reconstruct it in 3D without taking some liberties of guesswork. But here's my version. Morrow states that the rectilineator consisted of a number of sections in the form of double T-squares, each 12 feet in length with braced and tensioned crossarms 4 feet in length. The material was 1-inch mahogany, seasoned for 12 years in the shops of the Pullman Palace Car Company from Chicago. The horizontal bar was 8 inches in width and the crossarms 5 inches. He used steel tension rods marking an X across the entire section and extending through the extremities of the crossarms. They were adjusted to maintain the constancy of right angles. Finely trimmed brass facings at the extremities of the crossarms constituted the adjusting surfaces. Through flanges in the facing, ingenious screws were placed for securing the adjustments when made. Each section was supported by 2 strongly built, platformed standards, with adjustable castings to receive the horizontal sections between the body of the castings and adjustable cleats with clamps and set screws. The beams rested in the casting edgewise. The principle involved in its operation was as simple as the placing of 2 rectangular plates in contact, or laying 2 mechanics squares together. From the first to the last of the 1045 adjusted sections, the same procedure was methodically performed. 2 standards were placed in front of the previous adjusted section, and placing the castings at the approximate height. The new section was placed in position in the castings. Initially, they turned the set screws to raise or lower the horizontal axis to approximately the height of one of the middle brass lines of the previous beam. The brass facings were then brought to 1/4 of an inch of contact. Operators of the set screws were directed to raise or lower the section to bring the hairlines exactly coincidental. Fine lines were read with the microscope, and the section was carefully moved horizontally by 2 set screw operators turning each screw in unison as the facings get to 1/50th of an inch apart. Then a Bristol card is placed between each facing with equal friction to ensure exact spacing. When the same card passes through each facing top and bottom with equal friction, it proves that the adjustment is precise. Then finally, the 2 sections are bolted together at the 2 brass facings, top and bottom, with equal torque, and the procedure is repeated. They had watchmen guarding the apparatus continually throughout each night to ensure no one tampered with it. As expected, because measuring the curvature of the Earth will happen in a logarithmic fashion, increasing exponentially toward the end of the survey, there wasn't any detectable deviation for the first few sections. But after that, it was a done deal. As soon as the airline showed consistent deviation in the descent, the sign of curvature of the Earth already could be determined. And it was, of course, concave. What still needed to be determined was if the amount of descent was consistent with the circumference of the Earth, and it was. After 1 mile, it measured 8.02 inches, only 2/100ths of an inch away from an even 8 inches. That, my friends, is the work of a genius. After 2 miles, it was still fairly close, 30.62 inches to the generally agreed 32 inches. And at the end of the survey, at 2 3/8 of a mile, the descent was 48.25 inches. At every 12th adjustment, the spirit level was read. If the bubble began to deviate to the south, the Earth would show to be convex, and if to the north, then concave. The bubble consistently rose to the north of the vial. The plumb line was also used and hung over the 4-foot vertical crossbeams. In converse manner to the spirit level, if the bob shifted to the north, it would show convexity, but if to the south, then concavity. The plumb bob consistently shifted to the south again, further corroborating concavity. The 12-foot mercurial level would measure the angle of divergence within the length of the beam. This deviation would become more apparent at the end of the survey. Morrow also used the telescope to view the horizon from 15 feet behind the last section in the line. He noticed a continual sinking of the airline going below the horizon, which further proved the Earth was curving upward. There were 3 main measurements when all 4 of these appurtenances were used: one at 1 mile, one at 2 miles, and one at 2 3/8 of a mile. The results all agree in testimony of concavity. The remaining line-of-sight phase of the survey proved to show a fairly expected amount of descent as the airline passed through the excavated sandbar after Gordon passed to finally hit the water's surface. Morrow placed a steel horizontal strip at the height of the last recorded measurement protruding from stake 20 at the 2 3/8 mile mark, then moved back his telescope to stake 19, 1/8 of a mile away, where the heights of both markers were aligned to point through the excavated sandbar and wait for the bottom of the hull of the sailboat to line up. Through signaling, it was determined, and the crew on the boat calculated a 4 1/8 mile distance from the stationary tide register. The survey was complete and deemed a complete success. And the data speaks for itself. It wasn't tampered with. Even Simonek admits it appears genuine. And you begin to really see the lopsided victory for concavity when you take the numbers from the column distance of airline below secondary datum, or the amount in inches of deviation every 1/8 of a mile, and plot them on a graph. You see how accurately it matches the calculated amount of curvature to the Earth? It's truly a slam dunk victory, and a silent testimonial witness of the fact that you are living inside the spherical concave Earth.